Okay, so yesterday we were looking at the Frechet derivative. So the general framework is that I have an open set contained in a non-linear space. Yeah, please. And F is a mapping into another non-linear space. A belongs to U, and then F dash A, if it exists, belongs to the space of bounded linear maps from E to F, and you have the f of A plus H minus f of A minus f dash A H is little o of norm. So this is the framework. Now some properties of the derivative. The following properties are very obvious. First one, if you have f and g two maps, both differentiable at A, then of course f plus g prime A is f dash A plus g dash. That is very obvious. You just write this for the f, write this for g, add the two, you will get the result. Similarly, you have lambda is a real number, then lambda f dash at A is lambda times f dash. This again you can prove without any difficulty. Okay. So the first important, see, everything which you do in calculus must be valid, otherwise there is no point. See, you have to go further, generalize. So what you have you should not lose. So the one of the most important properties is what is called the chain rule. Sometimes when I was in BSc they call it function of a function rule. Okay. Okay. So theorem, f from U contained in E, f g from V contained in F to capital G. So here E, F, G are all non-linear spaces, U in E open, V in F open. A is in U such that 1 f of A belongs to V, and 2 you have that f is differentiable at A, and 3 g is differentiable at f of A. So A is a set point in on the open set U where f is defined, and f of A falls inside the set where g is defined, and then U is f is differentiable at A and g is differentiable at f of A. Then define H equals g composed with f on the set f inverse of V. F inverse of V, inverse image of open set is open for continuous map, and this is of course contained in U. Okay. F inverse of V is contained in U. So from this set I can define the composition map, because everything will go into V, and V I can compose with G. Okay. Then H is differentiable at A, and what is the formula for the derivative? So G composed with, so H dash A. So this must be a linear map from E to G. Okay. and I am going to give it as a composition of two linear maps. So, I have G dash at f of a composed with f dash at e. Here there is a composition. So, f dash of a goes from E to f, G dash goes from f to G. So, when you compose you go from E to G. So, this formula makes sense. Now, I have to do this. So, is the statement clear? So, you have a composition of two differentiable maps, and then you say I can, the composition is differentiable, and here is the formula for it. So, it is the composition of the corresponding derivatives. Okay. So, we can write f of x equals f of a plus f dashed x minus a plus epsilon times norm x minus a. Right. This is the definition of derivative. Similarly, g of y is so g of f of a plus g dashed, oh this is f dashed at a, sorry, g dashed at f of a into y minus f of a plus some eta of norm y minus f of a. So, what do you know about epsilon and eta? Epsilon of norm of x minus a, norm of this divided by norm x minus a tends to 0 as x tends to a, and similarly you have norm of eta of norm y minus f a. It's no norm, some error term. Okay. By norm of y minus f of a goes to 0 as y tends to. This is standard. I have not done anything other than apply the definition of the derivative. That is all I have written. So, what is h of x minus h of a? So, this is g of f of x minus g of f of a. So, I put y equals f of x and I use this relation. So, that will be equal to g dashed of f of a into f of x minus f of a plus eta of f of x. So, I am just substituting this relation with y equals f of x. Now, I have here the f of x minus f of a, for which I will use whatever is here. So, you have h x minus h of a equals g dash f of a. Remember, this is a linear operator acting on all these things here. So, that is f dash a x minus a plus g dash f of a acting on epsilon of x minus a. So, that is I have substituted all this for f x minus f of a here, and then I still have this plus eta of f of x. So, up to now I have done nothing. I have just applied the definition of derivative and substituted various things in the right place. Now, if you see, here is my formula, and I already have that in the first line. So, my theorem will be proved if I can show all this is little o of x minus a. Okay. So, to show all this is little o of x minus a. If I do that, then by definition that has to be the derivative. Okay. The first one is easy. So, norm of g dash f of a epsilon x minus a, that is less than equal to norm g dash f a norm of epsilon x minus a, and this is a constant, and this I already know is little o of norm x minus a. So, that is finished. So, that is okay. So, I only have to look at this one. So, norm of eta f x minus f a by norm of x minus a, I must show goes to 0 as, so does this go to 0 as norm x minus a goes to 0. Then it will be little o of norm x minus a, that is the definition of little o which we did so far. So, let us try to see that. So, norm of eta f x minus f a by norm of x minus a, of course, I will write as norm of eta f x minus f a by norm of f x minus f a into norm of f x minus f a by norm x minus. And I want to show that this goes to 0 as x tends to a. Okay. So, now let look at f dash a, it is some number. So, choose capital M positive such that this is strictly less than m. Then what do you know about norm of f x minus f a by norm of x minus a? As x approaches a, this should go to f norm f dash a, okay, by continuity, and this is a little bigger. That means, if x is close to a, this will be less than or equal to m if x is close to a. That is for some norm x minus a less than delta. When something goes to the limit and you have something little more than the limit, then just before reaching the limit, you will have to enter the compound wall before you reach the house. Okay. So, if you have that, so for all norm x minus a less than delta, norm of eta f x minus f a by norm of f of x minus f a, sorry, x minus a is less than or equal to this expression here, norm of eta f x minus f a by norm of f x minus f a into m. What does this also tell you? This tells you on the other hand that f x minus f a is less than m times norm x minus a. Okay. So, that means f x converges to f of a as x tends to a. So, for norm x minus a less than delta, f x minus f a will also be very small, and that means this is anyway little o, we know that, and therefore, this goes to 0 as x tends to. Okay, I have not written down everything here. This means I can make this less than as small a number as I please by choosing x minus a smaller than even delta if necessary. That is one. Because eta is already a little o. So, everything is of little o of x minus a, and therefore, this is the derivative. So, this of course, we will use left and right all the time. So, chain rule. So, even if you have difficulty with the proof, remember the statement, if you have two differentiable functions and you compose them, then the derivative of the composition is g dashed at f a into f dashed of a. Yeah, that is what I said. From now on, almost every theorem I will do will use this. So, you will see. Okay. So, now we were always claiming this is a course on calculus of several variables. So, that means Rn, Rm typically. So, we are now going to approach think of in terms of that. So, let us assume now f be the product of so typically think of r power m equals r cross r cross r m times, like that. So, let pi equals projection to ith coordinate. That means pi of x1 xn is xi, where any x in f you can write x equals x1 xm, where xi is in f. So, pi is a projection to the ith coordinate. So, pi is a mapping from f to fi. Similarly, I am going to define ui is a mapping from fi to f. What is ui of xi? It is 0, 0 and then xi 0, 0. So, this is the ith place. So, given xi in the ith coordinate space, I produce a vector which is 0 everywhere else except at the ith place it is this function. Then the two following things. So, if you first apply ui and then you apply pi, what will you get? If I apply ui, I will get this. If I apply pi, I will get xi. So, xi will go to xi. So, this is nothing but the identity map on the space F. What is sigma I equals 1 to m ui composition pi? So, what is take a typical vector x1, x2, xn. If I apply pi, what will I get? I will get xi, and then if I apply ui, I will get 0, xi, 0. Now, if I add them all up, what will I get? X again. Okay. So, this is nothing but identity on F. And of course, recall that pi, ui are all linear maps. Proposition. So, E non-linear space, U contained in E, U open. F equals F1 cross F. Fi are all non-linear spaces. So, you have the product norm on this. So, F is from U contained in E into F, and A is E. Then F is differentiable at A if and only if Fi, which is pi composed with F, is differentiable at A for all 1 less than equal to I. And in this case, F dash A equals sigma I equals 1 to m ui composed with Fi dash. So, let us first see if all these things I have stated correctly, okay, if the maps are going to the right places. F is from U to F and pi is from F to Fi. So, pi composed with F is a map. So, Fi is a map from U to Fi. So, I can talk of the differentiability at a point in that case. Then what is Fi dash? This belongs to L of E to Fi. So, Fi dash takes E to Fi, ui will take Fi to back to F, and therefore, this composition will take E to F, and this is in the right place. Okay. So, this equality is correct, at least as far as the spaces and the mappings are concerned. Validity of it has to be proved. So, proof. Suppose F is differentiable. Now, pi is a linear map, and we have seen yesterday that all bounded linear maps are differentiable. That was the first example we did. So, by the chain rule, pi composed with F equals Fi is differentiable. When you compose two differentiable maps, so it is differentiable. Conversely, Fi differentiable for for all I. Now, f, where does it go from? It goes from U to capital F. Okay? And if I compose it with the identity here, I will get back f only. But identity of f, I have a formula here. Okay? So, this is nothing but f is nothing but sigma ui composed with pi composed with f. Right? I am just composing f with the identity map. For identity map I have this formula, and therefore, f is nothing but this. But what is this pi composed with f? Fi. So, this is sigma ui composed with Fi. Fi is differentiable, ui is a linear map, therefore, it is differentiable everywhere, and therefore, ui composed with Fi is differentiable, sum of differentiable functions is differentiable, and therefore, f is differentiable. You think it is different? I take a map, I compose it with the identity, the map will not change, right? It will still be the same. Okay. So, now let us compute starting from this. So, now I know that f is differentiable if and only if fi is differentiable. Okay. Now, let us compute the derivative. What is the derivative? So, f dashed at A is sigma I equals 1 to m, because the derivative of a sum of mappings is nothing but the sum of the derivatives. So, ui composed with fi prime Okay. Now, apply the chain rule. So, you have a composition of differentiable maps. So, what is the derivative in each case? So, equals I equals 1 to m, ui dashed at f dashed I of a, fi of a, but ui is a linear map. So, where we said derivative of a linear map is a constant, that means it is the same everywhere, it is itself. So, the derivative is just ui composed with derivative of fi at a. So, by the chain rule we get this formula, and that is exactly what we have here. So, we have used the chain rule repeatedly, and we have used the fact that for the linear map, whatever may be the point, the derivative is itself the same linear map. What does this actually mean? See, we wrote a formula here, f is, where did I write it? Yeah, f equals sigma ui fi. What does it mean? F of x, it is a m tuple, right, because it goes into a product space. Okay. Now, fi of x, if I apply ui, that means I will put fi in the ith place and 0 elsewhere. Now, I do this for all I and then I add up. So, I will get f1 right. So, when you have a mapping which goes into a product space, all I am saying is it is differentiable if and only if each coordinate mapping is also differentiable, and the derivative f dash of a is nothing but f1 dash of a, f2 dash of a, fm dash. What does this mean? This means if I apply f dash a to any h, it must go to f, which is a product space, and that point will be just f1 dash a of h, f2 dash a of h, fm dash a. So, it is very easy. If the domain range space is a product space, then the derivative is nothing but you simply take the coordinates as the derivatives of the coordinate functions. Now, let me take E as a product space. Okay. So, let E equals E1, E2, En, Ei are non-linear spaces. So, x in E means it is equal to x1, x2, xn, xi in Ei, Pi is the projection, and Ui is the same as before, and therefore, you have all these. So, this is I of Ei and this I of E. So, now your domain is a product space. So, I want to know how to write the derivative of a function in terms of some other functions. So, now I am going to define. So, let U contained in E be open and A in U be fixed. So, A equals A1, A. This corresponding to this, I define lambda I from Ei to E. So, already I have Ui, I have defined. Now, I am going to define E to E. Yeah. Nothing changes here. It is whatever I wrote for F, you write for E. Now, the only new thing is fixing I am going to define a function lambda I, which depends on this, and this is given by lambda I of xi. So, you already I have a ui, okay, which is with respect to the origin. Okay. So, this will be now a1 up to ai minus 1, ai plus 1 to an, and in the ith place I replace ai by xi. So, I fix a point A. So, if it were the origin, then lambda I is the same as that ui function. But for every point A, I am defining a function lambda I which depends on A. I keep on saying that, namely you simply replace the ith coordinate of A by a variable xi. So, I suppose you know where I am going. Okay. We are trying to come to the notion of a partial derivative, because okay. What do you do for partial derivative? You freeze all the other components, only one component is allowed to vary. So, I am trying to do that process now. It will be clear in a few minutes what I am doing. Okay. So, proposition U contained in E open A in U, E equals E1 cross En, and F is of course a non-linear space. EI are non-linear space. And F is from U to F. Then F is differentiable at A implies, so this is not a if and only if statement, this is only a one way statement. Okay. F composed with lambda I is differentiable at AI. For all 1 less than to I less than. And in this case, f dashed of A acting on H, which is equal to f dashed of A acting on H1 to Hn, because H itself is in E and therefore, it is a n tuple, okay, equals sigma I equals 1 to n f composed with lambda I prime at AI. So proof is very similar to the earlier one. What is lambda I at xi? This I said was A1 to AI minus 1 xi AI plus 1 to an. And this is nothing but A plus ui of xi minus a. Ui with this will put zeros here and xi minus ai here. If I add this, I will get this. And ui is linear, so this you can write as a plus ui of xi minus ui of a. So, what is lambda I? This is just ui plus a constant being on this. So, lambda I is differentiable because it is a linear map plus a constant. So, lambda I is differentiable and lambda I dash is nothing but ui, because we saw this yesterday. If you have a linear map plus a constant, the derivative is always the linear map. So, f differentiable implies by the chain rule f composed lambda I is differentiable. chain rule tells you if you have a composition of two differentiable maps, then then it is also differentiable. And what is F composed with lambda I dashed at A I? This is F of F dash at lambda I A I composed with lambda dashed I at by the chain rule. But what is lambda I of A I? It is the point A itself, because if I put A I here, I will get back A. So, this is nothing but F dash A, and lambda I dash we saw is just U I. Now, you have this relation here, sigma ui pi equals. Now, you compose with f dashed a. So, you get sigma f dashed of a composed with ui composed with pi equals f dashed. Okay. And f dashed of a composed with ui is exactly f composed with lambda I dashed at a I and what expand this, apply it to any h, what will happen? F dashed of a at h equals sigma f composed with lambda I dashed at a I composed with pi acting on h. But what is pi acting on h? It is a projection to the ith coordinate, and so this is f composed with lambda I prime at a I. Okay. Now, what suppose you are in Rn, okay. So, let us take E equals Rn. Then what do you mean by f composed with lambda I dash? That means you are taking a point A and then you are replacing the function as f of a1 ai minus 1 xi an ai plus 1 etc. an. You are replacing ai by xi and then you are differentiating it. What is that? That is precisely the partial derivative of the function. So, this is precisely df by dxi at E in the usual language. Okay. So, for the same reason we will call these derivatives as the partial derivatives of f at A. Okay. So, definition: f composed with lambda I dash at a I is the ith partial derivative of f at A and is denoted df by dxi. So, now let us go to that formula and see. So, now I am going to take E equals R n only. Then what does that formula say? F dash at A acting on H is equal to sigma F composed with lambda I dash at AI into Hi, I equals 1 to n. And just now we saw that this is nothing but the usual partial derivative here. So, you have that is equal to sigma I equals 1 to n df by dxi. So, if f is differentiable, then all the partial derivatives exist and the derivative can be computed using this. So, what do you mean? Suppose I have f is a real valued function. So, f goes from Rn to R. Then what is f dashed of A? This belongs to L of Rn to R. But that is the dual space of Rn. But what is the dual space of Rn? Yeah, but what is that? You know that. It surely must come in your linear algebra. Linear functions from Rn to R. What is that? This is isomorphic to Rn itself. What are all the linear functions from Rn to R? This is nothing but of the form sigma ai xi, the planes. Okay. These are all the linear functions. So, every linear functional is uniquely determined by these constants ai or alpha I if you like. Okay. So, every linear functional is given by n constants and so it is isomorphic to Rn. Okay. I am sure you have seen this before. Linear mappings from Rn to Rm will be matrices. Here m equals 1, so it is just one row. Okay. So, you can think of f dash A should be a vector actually, and that is nothing but df by dx1 at A, df by dxn at A, and this is a familiar symbol, you have grad f. How do you understand this? By what we understand is this relationship. When I say this, I mean this. So, now let us look at a map from Rn to Rm. So, now I am going to combine the two theorems which I proved now. First one was when the range space was a product space. The second one was when the domain space is a product space. Now, let us take both. Okay. So, f u in Rn going to Rn. I have rubbed it off here. So, by the first theorem, because this is a product space, we can write f of x equals f1x fmx, right. But because I am now I want to use matrix notation, so I am going to write this as a column vector. then what did I say the derivative was f dash of x at any h at a sorry, equals f1 dash a at h fm dash a at h. This was the first theorem. We saw this, right. The first proposition I proved is when the range space is a product space, and then this is exactly the formula I got. Now, I use the fact the range is now real, but the domain is a product space, it is Rn. So, each of these can be written using this formula. Okay. So, this is equal to what is f1 dash a h, which is df1 by dx1 at a h1 plus df1 by dx2 at a h2 plus df1 by dxn at a hn. Similarly, I write for all of them. So, this is dfm by dx1 at a h1 plus dfm by dxn at a hn. Now, we write this as a matrix. That is equal to so f dash of a, which is a linear map from Rn to Rm, right. The derivative should be a linear map from Rn to Rm. Therefore, it can be given by a m cross n matrix, and this is the m cross n matrix. Called the Jacobian matrix. So, f dash a at h is a vector which is given by the product of. So, this we reconcile what we do using partial derivatives to with this notion. So, what is the derivative? It is nothing but the Jacobian matrix acting on this. When you are looking at maps from Rn to R. Okay. So, next important result is called the mean value theorem. What does it say in one dimension? Suppose you have a function f which is differentiable in the open interval, continuous on the closed interval, then fb minus fa is some f dash of some c times b minus a, where c belongs to the open interval a. This is the classical Lagrange mean value theorem. Now, this you cannot extend in general to the general situation when you are dealing with vector valued functions. For instance, let me take the map from R to R2. F of t is cos t sin t. Then according to our calculation, what is f dashed at any point? You have to just take the derivatives of the individual functions. So, that is minus sin t cos t. Now, f of 1 equals f of 2 pi. Right? F of 1 equals f of 2 pi. Sorry, 0. Yeah, f of 0 equals f of 2 pi. Okay. So, according to this mean value theorem, I must get f of 2 pi minus f of 0 is some f dash c acting on 2 pi minus something, right. But this f dash c can never be 0, because this is 0. So, f dash c has to be 0, but what is f dash c? Minus cos t sin t, its modulus is always 1, because cos square plus sin square is 1. So, it can never be 0. Okay. So, you cannot expect any such theorem like this. What one can get is, on the other hand, look at this, take the modulus f b minus f a less than equal to or equal to mod f dash c into b minus a. This is less than equal to sup of mod f dash t b minus a, where t belongs to a b. Correct? I have not done anything new. Okay, I have started from this relation. I write this. This is less than the maximum. Okay, so now this, in this form, we can write the mean value theorem. Okay, so mean value theorem is valid in this form, not in this form, and even in this form, it is a very, very, very powerful result. Okay. Okay. Instantly, this itself, even in one dimension, it is very useful. Suppose you want to show that sin x minus sin y is less than or equal to mod x minus y. How will you do? Derivative of sin is the cosine. Okay. So, mod sin x minus sin y is less than or equal to mod x minus y into maximum or supremum of the derivatives, but derivative is always less than or equal to 1, and so you have this. So, this is a very nice way of proving such inequalities. So, you can do it even for sin square. Sin square x minus sin square y, apply mean value theorem, it is less than mod x y into sup of the derivatives, but what is the derivative? 2 sin x sin y, which is sin 2x, which is also less than or equal to 1, and therefore you still have this. So, this is a very nice quick way of getting all these inequalities. So, mean value theorem is a very powerful theorem which allows you to do many things. We will see applications of it also. So, now let me see if I can prove it for you. So, theorem This is the mean value theorem. EF norm linear spaces and U contained in E F T F. So, you define AB, the interval, as set of all x in E, such that x equals 1 minus t times A plus t times B. So, it is a line segment connecting A and B. Okay. So, assume AB is contained in U. Assume f is differentiable on at each point of A. Then norm of FB minus FA. Yeah, because it is still a point inside the open set, no? I am taking a point inside the open set. So, this less than or equal to sup norm f dash t f dash x, x is in AB, times norm B minus. Okay. So, I will rather like to concentrate on the applications of this result than in the proof of this itself. So, I will skip the proof of this and let us see some nice applications of this, because this we do not have enough time. Okay. So, corollary, U contained in E convex and open. F differentiable at every point of U, and norm f dash x is less than or equal to k for all x in U. Then if x1 and x2 belong to U, we have norm of f of x1 minus f of x2 less than or equal to k times norm x1 minus x2. Okay. Why? So, proof. So, if x1 and x2 belong to U, U is a convex set and therefore, the x1 x2 is contained in U, since U is convex. What do you mean by a convex set? If you take any 2 points, a line segment containing those 2 points is. Therefore, by the mean value theorem, norm of f of x1 minus f of x2 is less than or equal to sup of norm f dash x, x in x1 x2 times x1 minus x2. But on the whole set itself I know that f dash is less than or equal to k, and therefore that is like k times x1. This is exactly like that sin square x sin x example I gave you. Okay. Next corollary, if U is a connected open set in E and f dashed is identically 0 on U, then f is a constant function. So, this again generalizes what you know, that if the derivative of function is 0 in a connected set, then the function is a constant. Okay. So, this is true even in non-linear spaces. You take a connected open set. Okay. So, what is the proof of this? So, proof, so you take any x naught in U. So, there exists a ball, center x naught and radius epsilon, which is contained in. That is the definition of an open set. But a ball is an open set and it is also a convex set. And what do you know about the derivative? It is identically 0, and therefore, the norm of the derivative is also 0. So, it is a bounded function. That means, therefore, f of x1 minus f of x2 equal to 0 for all x1 x2 in B x naught epsilon. That means, this function is locally a constant. So, if you take a point in any neighborhood of it, it is a constant. Now, you take any B in F, what can you say of f inverse of B? It is an open set because of all this. You take any point in f inverse of B, take a neighborhood of it, then I showed that it is a constant, so it will still take the same value B, and therefore, it is an open set. But this is a Hausdorff space, and therefore, f inverse of B is also closed. Inverse image of a single point is always a closed set. So, f inverse of B is always open and closed, and U is a connected set. Therefore, for every B, either f inverse B is all of U or f inverse B has to be empty. Now, take a point x naught in U and take f of x naught, then f inverse of f of x naught is not empty. So, it will be all of U. So, U is a function is a constant. So, these are all applications of mean value. Now, we are going to do one very big application of the mean value theorem. So, theorem E equals E1 cross En, Ei are all nonlinear spaces, F is a nonlinear space, and U contained in E open, and F is from U contained in E into F. Okay. Now, yesterday we saw examples of a function which has directional derivative in all directions, but the function is not differentiable. So, automatically it follows that if a function has all its partial derivatives existing, it still need not be differentiable, because what are partial derivatives? They are only derivatives in certain fixed directions. Okay. So, when can you say if the partial derivatives exist, then the function is differentiable. Okay. So, this is I said yesterday some extra continuity is needed. So, I am going to state that precisely now. Assume df by dxi x exists for all x in U. So, partial derivatives exist not only at one point, but they exist at all points. Okay, it need not exist at all points, it is enough if it exists in the neighborhood of some point. But so for all x in a neighborhood of A in U. Okay. And assume finally x going to df by dxi of x is a continuous map for all I in that neighborhood. Okay, so this is the extra condition. So, the derivative partial derivatives do not exist just at one point, they exist in a neighborhood, and x going to that partial derivative is a continuous linear map, continuous map there. Then f is differentiable. So, with these extra conditions, you deduce the differentiability from the existence of the partial derivatives. Hmm? Mm. 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 It will not be constant. No? Think of this, take 1 comma 2 and 3 comma 4, 2 disjoint intervals, okay, and define f of x equal to 1 in 1 2 and 2 in 3 4. This function is differentiable, derivative is 0 everywhere, but it is not a constant function, it is okay.
If U is open and E derivative is 0, can you say f of x is equal to 0? F of x is equal to, sorry, f of 0, f is 0, f is equal to what?
Nothing.
Can you say f is a constant function?
Constant on every connected component, that is all you can say. Constant on every connected component. So, on different connected components it can be different constants.
And can you say the function, if the function is, the derivative of the function is bounded, can you say f is bounded?
What about f of x equals x? Derivative is 1, it is very much bounded, but the function f of x equals x is unbounded function on the real line, no? Yeah. So, derivative bounded does not, it only says it increases at a certain rate, but it can keep on increasing if you have enough space.
So, through the derivative we can predict the
No, unless your set is also bounded, compact, then yes. Because then by mean value theorem f x minus f y will be less than mod x minus y times that constant, and x minus y itself is bounded because it is a compact set, and therefore, the function is bounded. Yeah, because I take any point in f inverse of b, I take a ball round it, then I just now showed you that every point in the ball has the same value. So, f inverse of b contains a ball around every point in it. So, f inverse of b is an open set. Okay. So, proof. So, if f is differentiable, I know how to calculate its derivative, because f dash of a equal at h is sigma df by dxi at a hi. This is compulsory. If it happened, then I know, because it is a product space and all the partial derivatives exist. We have already shown that if it is differentiable, then this happens. So, I have to show now, so I know the candidate. So, I have to show if the candidate is okay or not. Okay. So, what must we show? So, to show f of x1 xn minus f of a1 an minus sigma I equals 1 to n df by dxi at a xi minus ai is little o of norm of x. Suppose I show this, then I am through, because by the definition of derivative, this is linear in x minus a, and therefore think of x minus a as h. Okay. So, then this is linear term here, and I have little o on this side, and therefore, this has to be the derivative. So, this is all I have to show. To show that, so if f is differentiable, I know what the candidate is. So, I take the candidate and see if it verifies the definition of derivative or not. Okay. To show that it verifies the definition of that, I just have to check this identity. So, we are going to write this in a nice way. So, I write f1 x1 minus xn minus f of a1 x2 xn minus df by dx1 of a x1 minus a1 plus f of a1 x2 xn minus f of a1 a2 x3 xn minus df by dx2 a x2 minus a2, and so on. And finally, f of a1 an minus 1 xn minus f of a1 an minus df by dxn at a xn minus a. So, all these terms, cross terms will get cancelled. So, this first minus last is retained, and this one I have distributed one for every line. Okay. I will show that each line is little o of x minus a. So, then the whole thing is little o of x minus a, and that is done. So, let us show that each line is little o of x minus a. So, let xi 1 belong to E 1, and I define g of xi 1 equals f of xi 1 x 2 xn minus df by dx 1 at a xi 1 minus a 1. Then what is the first line? First line is nothing but g of x1 minus g of g of x1 will be f of x1 xn minus df by dx1 x1 minus a1. F of a1 is g of a1 is this, and this part will give you nothing because a1 minus a1 is 0. Now, G is differentiable. What is G dashed at xi 1? This is nothing but df by dx 1 at xi 1 x 2 x n minus df by dx 1 at a. Because here if I differentiate xi 1 I just get 1. So, I just df by dx 1 at a minus this. So, let epsilon be greater than 0. Now, I am going to use the hypothesis that the derivative is continuous, partial derivatives are continuous. That means, so df by dx 1 continuous in a neighborhood of A implies there exists a delta positive, norm of x minus A less than delta implies norm of g dash xi is less than epsilon. G dash xi is just the difference of these two, just definition of continuity. Okay. So, what does it mean? Now, therefore, g x 1 minus g a 1 by the mean value theorem is less than the supremum of the derivatives times x minus a. So, this is less than or equal to, but the derivative is always less than epsilon into norm of x minus a in a neighborhood, that is norm x minus a less than delta. That means, first line is little o of norm x minus a, because if I divide the first line by norm x minus a, it will be less than epsilon whenever norm x minus a is less than delta. That is exactly saying first line is long. Similarly, every line you can do define. So, similarly every line, and that proves the theorem. Okay. So, if you have the continuity of the derivative, and so the important thing here is because of the continuity you are able to show use the mean value theorem. Okay. So, this is a very nice application of the mean. So, already we have seen 2 or 3 applications of the mean value theorem, some more will follow later. I mean its mean value theorem is something which will pop up again and again and again in every. Okay. So, we will stop here, continue in the afternoon.